Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics for Hart University of Science and Technology. I welcome you to the course PHY 103 Waves and Oscillations. Today I will be covering the 16th lecture of this course, and the topic is standing waves and resonance. First, I will give the learning objectives. For two overlapping waves having same amplitude and wavelength that are traveling in opposite direction, the student will understand from the sketch of various snapshots, and they will be able to find out the resultant waves indicating nodes and antinodes. Also, the two overlapping waves having the same amplitude and wavelength traveling in opposite direction, they will be able to find out the displacement equation for the resultant waves, and also they will be able to calculate the amplitude in terms of the individual wave amplitude. Also, to describe the simple harmonic motion of string element at an antinode of a standing wave. Also, to describe the resonance on the string tied between two supports, and sketch the first several standing wave pattern indicating nodes and antinodes. In this course, we are following the book Fundamentals of Physics by Holliday, Resnick and Walker, 10th edition. Some of the figures are taken from this book. Now, if you remember, in our last two lectures, we have discussed the interference of waves, and in that lecture, I think it was lecture number 14, we have discussed the traveling wave moving in the same direction. So we discussed two sinusoidal waves of the same wavelength and amplitude traveling in the same direction along the stretched string. But now we are discussing the standing wave. So for that, we start with this question: what if they travel in the opposite direction? By they, I mean the two sinusoidal waves. So previously we have already discussed the resultant waves of two sinusoidal shaped waves having identical wavelength and amplitude traveling in the same direction. In this lecture, to cover the standing waves, we will be discussing the same sinusoidal waves of the same wavelength and amplitude, but now they will be traveling in the opposite direction. So we can again find the resultant wave by applying the superposition principle. So before going into the mathematical part, first we want to see the outcomes of two sinusoidal waves traveling in opposite directions. So here in this first figure, in the A part, a wave traveling to the left, and we have another wave which is traveling to the right. Now, in order to have a standing wave pattern, these two waves should have the same wavelength and amplitude, and also they need to superimpose each other. That is, they are just, for example, traveling on the same string but in opposite direction. So they will, at a given point, they will encounter, and let's say we took this resultant wave snapshot when t is equal to 0. That is, we get t is equal to 0, a pattern like this, such that the peak matches the peak, and these depth of this wave which is traveling to the left exactly matches the depth of this wave which is traveling to the right. So in that situation, for example, the first snapshot, or say a picture taken when t is equal to 0, that is the resultant wave amplitude is now double the amplitude of the incident traveling wave. Now we may have just a straight line. This is this blue pattern just representing a string over which two traveling waves of oppositely directed waves are approaching each other, such that at t is equal to 0, the string is having this kind of a shape, and also when t is equal to 1 over 4 t, remember this t is the time period of these identical traveling waves. So at times t is equal to 1 over 4t, there is another snapshot of the string over which two traveling waves are approaching, and one can have just a horizontal line, that is zero transverse displacement. Also, if we take another snapshot at t is equal to exactly half the time period, such that we have this kind of situation resulting in this kind of standing wave, such that it is just an identical, but now the depth comes first and also the peaks are here. Still the resultant amplitude is double. Now if we take another snapshot, again we get a zero displacement line relative to the transverse direction in this situation. If we take another snapshot exactly at this time, so that we'll be getting again a zero displacement. Now if we take another snapshot at t is equal to exactly equal to the time period, we start with t is equal to 0, right? And again we get the same identical. Now these two shapes are the same as we took the t is equal to 0 snapshot. So if we see the outcomes, that is the C figure, one can have a double amplitude resultant wave, a zero amplitude, again maximum amplitude or minimum amplitude. So we have maximum and minimum outcomes of the resultant waves. Now these outcomes, or we can say the resultant wave, which is just a representation of the string over which these traveling waves are approaching each other. Now over this there is those black dots. These dots represent the nodes that we will discuss on the next on the next slide. That is, if you remember in our last few lectures, we have discussed that if you just send a sinusoidal wave on a string, each element of the string just performing simple harmonic motion, that is, it just move up and down through that equilibrium point. But in case of the standing waves, these portion that is in between the nodes, these portion are these elements of the string are performing a harmonic motion. That is, let's say at t is equal to 0, it was these elements were going up. When t is equal to 144, they are just equal to have the 0 amplitude, and again it just goes to the other side. So that in between the two nodes, these are the two nodes. Here it is having m is positive, and on this side it is negative. That is just going up and down. But these points which are represented by these black dots, they are known as nodes, and they are not moving. That is, they are points on the string having zero displacement. So that is different than the traveling wave situation, and that's why they are now known as the standing waves, because some portion are still performing simple harmonic motion, but there are some point on the string which do not move. So now after this brief introduction to the outcomes of or we can say the resultant wave of two sinusoidal waves approaching each other having identical amplitude and wavelength, we will discuss the outcomes. Now this is just the outcome, or just we can say the 5 snapshot that we took when t is equal to 0, t is equal to 1 over 4, t is equal to 1 half t, and then 3 by 4 t, and t is exactly equal to the time period. Now there are some interesting features. That is, the resultant wave is that there are places along the string, as I told you, called nodes, these black dots, where the string never moves. They are just stationary points. 4 such nodes are marked by dots in the above figure. That is, this one, this one, this one, and this one. These are the 4 dots across all the snapshot. See, all these 5 figures are taken, or we can say the snapshots are taken at different times, but at all times these parts are not moving up or down, they are just stationary. Halfway between the adjacent nodes are antinodes. These are the antinodes halfway between, where the amplitude of the resultant wave is maximum. These maximum amplitude points are known as the antinodes. So those points which are in between the nodes are performing simple harmonic motion with different amplitude. Remember, for example, this will go up and also it will go down, but this point will be having the maximum displacement. Wave patterns such as shown here are known as the standing waves, as I told you, because the wave pattern do not move left or right, they are just moving up and down. This pattern are just moving up and down, they are not traveling, and that's why standing wave do not carry any energy. So we can say that if we have 2 sinusoidal waves of the same amplitude and wavelength traveling in opposite direction along the stretched string, their interference with each other produces a standing waves. Now we will see the mathematical steps of these profiles known as the standing waves. So for that we will start with the 2-wave equation which we have discussed in this course right throughout. Let y1 is a wave, sinusoidal wave having amplitude ym and wave number k and frequency omega. Now the second wave, which is y2, having identical amplitude, frequency and wave number, but with this positive sign, it means they are just moving in the opposite direction. Let's say the first one is moving towards the right, the other one is moving towards the left, so that they approach each other, and the superposition principle will give us the resultant waves. Now, which can be solved using the same sine alpha plus sine beta formula. So one can simplify this expression to find out the resultant waves, which is a standing wave now. Now, this is a standing wave where this portion is just representing the amplitude, and again this is oscillatory in nature. Now this is a standing wave solution. Just to compare this result with the traveling wave solution, if you remember, we start with the traveling wave in this course, and we know that if y is having of this this function where h represents the function, let's say this is just a harmonic function but having kx minus omega t. Now this solution is not of this kind. If you remember, last time we have discussed the outcomes of two traveling wave, sinusoidal wave moving in the same direction. So in that situation we get a traveling wave solution, but once the wave are traveling in opposite direction we get a standing wave solution. So that's why these are just standing waves where the amplitude do not depends upon time, but this amplitude is different at different x. And that's why we have the nodes and antinodes that we are discussing on this slide now. So we will discuss the standing wave solution that comes through the superposition principle for wave, sinusoidal waves having identical amplitude and frequency traveling in the opposite direction. So we are now discussing this result. Now this amplitude 2ym sine of kx, the amplitude is 0 for values of kx that gives sine kx is equal to 0. If you remember, those points will be known as the nodes, as we have discussed on the graph. That is, if this sine kx is 0, so the amplitude will be 0. Now those points are known as nodes. So when this sine kx will be equal to 0, so we need to find out the value of kx. So if this kx is equal to n lambda such that this n is equal to 0, 1, 2, 3 just in integer, so that if n is equal to 0 it means kx is equal to 0. So when kx is equal to 0 we know that sine 0 is 0. So in that situation we will be having a node for this kind of wave, for these kind of waves. Again, if n is equal to 1, so that means we'll be having sine pi, let's say that will be having minus 1, so there will be a dip. Remember, this is amplitude or just a positive number, so if we take the modulus of this, so we'll be having a positive number. Still 2 and 3 and we'll be getting the rest of the nodes and antinodes. The nodes. So what are those points on the string locating at different x? As I told you, different x will give us different amplitudes at different times, because this is a harmonic function. So if we just convert this k to lambda by 2 pi over lambda, that is k is just the number of waves, number of wavelength in 2 pi radian. So in that situation one can have by just putting 2 pi over lambda instead of k and then solving it for x, so that x will be equal to n lambda over 2, such that n is equal to 0, x is equal to 0, x is equal to lambda over 2, lambda over, and then putting n is equal to 2, that will be equal to lambda. So all those points for which x satisfy this this relation will be nodes on that string. Similarly, the amplitude of those points will be having maximum, that is 2ym, if this sine kx is equal to 1. So sine kx is equal to 1 corresponds to the antinodes, and that will be for the kx is equal to half pi, 3 over 2 pi, or 5 over 2 pi. That is, if we rearrange this in terms of an integer n plus half pi, such that when n is equal to 0, 1, 2, 3 will be the different antinodes. So these are just the mathematical descriptions of those snapshots that we have discussed earlier, over which a string is having two traveling waves in the approaching each other. So if we just in the same manner convert this k to lambda, so in that situation we will be having x is equal to n plus half lambda over 2. So this condition for x is for nodes and this one is for the antinodes. Important thing is that these conditions are not fixed for nodes and antinodes. For sinusoidal profile having sine profile, these are the points for the nodes and antinodes. If we just change the profile of the incident wave, let's say this is cos of kx, and similarly this is cos of kx plus omega t, so this condition will change. But the distance between the nodes and antinodes will be fixed. That is, antinodes are separated by half lambdas and are halfway between nodes. This will be fixed for all kinds of waves, but these conditions will change for once we are changing the profile of the incident traveling waves. Now, these standing waves can be set to resonate, but before going into the resonance part, let me complete just one thing, that nodes are those points, as I told you, which do not move along the string as we have discussed, and that's why these standing waves do not transport the energy, but they are just there are some points which are fixed on the string and other which are just performing a simple harmonic motion with fixed amplitude. So that's why the energy is not transporting. But in case of standing waves, traveling waves, we have discussed that all the elements or all the particles of the string will just performing simple harmonic motion, and hence the energy transport through that string. Now, as I told you that one can resonate the standing wave profile by the following setup. That is, standing wave on a string can be set up by reflection of traveling wave from the ends of the string. Now, if an end is fixed, that is, you have a string and that is connected to a fixed end, so that if you are sending identical sinusoidal waves, so that they will be reflected, and those end points will be known as the nodes, because those points will not be oscillating because of the rigidness. This limits the frequencies at which the standing waves will occur on a given string. That we will understand in a minute with the help of the figure. Each possible frequency is a resonant frequency, and the corresponding standing wave pattern is in oscillation mode. So in your book, this figure is given. You need to read out those commentary, but let's say for this fixed end, over which you have a rope of length L, a string of length L with fixed ends. The resonant frequencies are, for example, once you have this one antinode and you have two nodes, so for that situation we have the frequency equal to f over lambda, that is, frequency is equal to the velocity divided by the wavelength. Now, in this situation, this lambda can be expressed as lambda will be equal to 2L, and this n is 1, 2, 3, such that for this situation L is equal to lambda, and that will be 2 lambda over 2. Now the oscillation mode corresponding to n is equal to 1, that is in this situation when you have n is equal to 1, that is known as the fundamental modes or the first harmonics. And also for n is equal to 2 and so on, you have different harmonics. Now the resonance will be discussed once we start the sound waves, and there we will be discussing the various harmonics. For the string it is just introduced, and you need to just read those commentary here. Now you need to follow this module which is based on the standing waves and resonance. Now this portion of the problems in your chapter 16, you have 20 problems. Problem number 42, problem number 60, you need to solve these problems which are just based on the standing waves and resonance. And with this, I thank you for your time.